Okay, in this video, I'm going to go through the Edexcel A-level Chemistry Paper, Paper 3, and I'm just going to go through the first part of this. Okay, right, so this question is about some halogens and their compounds. Okay, the intermolecular attractions between halogen molecules of the London forces. Describe how London forces form between halogen molecules. Okay, for 3 marks. So right, so if I just draw, you wouldn't draw it in an exam, you just describe it. So here is, say, a Cl2 molecule. Right, so you're going to say there are random fluctuations in the negative charge cloud. So at any one time, there can be an instantaneous dipole. Instantaneous dipole. So that means due to the negative charge cloud constant fluctuating, there might be a little bit more negative charge on this end of the molecule, and that would mean there'd be a slight partial positive charge on that end of the molecule. What that would do, the instantaneous dipole then, to a neighboring chlorine molecule. Okay, so here, because it's delta negative here, that would induce a partial positive here, and it would make the negative charge cloud move away, so you get a partial negative charge there. So you would get an induced dipole. And the London force is the attraction between the instantaneous dipole and the induced dipole. Okay. Right, the boiling temperature of chlorine and bromine is shown. The temperature. Explain why bromine has a higher boiling temperature than chlorine. Well, bromine is a larger molecule. It's got more electrons. And that means there are more points of contact between the bromine molecules. And they're closer together. So there's more parts of the molecule or neighboring molecules which are closer together, so there's more chance for London forces. More electrons, more points of contact. Okay, a student carries out experiments to determine the order of reactivity of the halogens, bromine, chlorine, iodine, and you've got the following solutions. So you've got bromine and iodine, and you've got the halogens, and you've got these halides. These are the elements. Okay. It doesn't have any access to chlorine or chlorine water. Uses cyclohexane as an organic solvent to identify the halogen present at the end. The student carries out the smallest number of experiments required to determine the order of reactivity of the halogens. Okay, so let's start off with you would get aqueous Ki, and you would react that, well, you would mix it with iodine. Okay, now there'd be no reaction there, of course. Sorry, let's leave that. Let's not do that one because it's a bit of a waste of all our experiments. Let's react it with the bromine. Okay, and you would get a reaction there. You would get bromine, of course, is more reactive, or if you like, the bromine likes the electrons better, so that forms a bromide ion. So you're going to get 2 kBr plus I2. Now, how do you identify? You've done that. How do you identify which halogen you've got there at the end of the experiment? Because iodine and bromine in aqueous solution both look a bit browny. It's not immediately apparent which one you've got. So what you'd do is you would get your aqueous solution, and you would add some cyclohexane to that, and then you'd shake it up. And what would happen is, to show you've got iodine there, the cyclohexane layer, which is the top layer, that would go, let's have a purple color, that would go purple, and that would tell you that the iodine in cyclohexane looks purple. That would tell you that you've got halogen there. Okay, so this reaction would tell you that bromine is more reactive than iodide. Right, now let's try and prove that bromine is less reactive than the chloride. So let's mix up Br2 with KCl, and there's no displacement reaction occurs there because bromine can't can't take the electrons off the chloride ions, no reaction. So you would end up with a test tube with bromine in it. Again, you would add, to identify it unambiguously as bromine, you would add some cyclohexane, you'd shake it, and you get that orangey color, and that would tell you that you had Br2 in the cyclohexane layer. So that would tell us that chlorine is more reactive than bromine. Okay, and then we've determined the order there really, because we've the first one we've determined that bromine is more reactive than iodine, and the second we've determined that chlorine is more reactive than bromine. So we've done it there. Right, it says include ionic equations, and I've given full equations there. So for ionic equations, obviously, I'm going to write down for any reactions that occur, well, the only reaction that does occur is that top one. So we want 2I minus plus Br2. The bromine takes the electrons off the iodide ions, become reduced, oxidizes the iodine to I2. Okay, so that's all you need to do for that one. Right. So how to make lactic acid, which is 2-hydroxypropanoic, okay, can be made from ethanol in a two-step synthesis. Okay, so let's write down lactic acid. I'll draw it over to the right, actually. Okay, so that is lactic acid, and we're going to start off from ethanol. Now, immediately, so we're going to have to convert it into some kind of intermediate and then convert it into there. Well, you can see straight away that we've increased the number of carbon atoms from 2 here to 3 here. We've lengthened the carbon chain, so we are almost certainly going to have to use a cyanide ion, okay, to do that. Now, we are going to react the cyanide ion. That was going to go nucleophilic attack on that carbon there. It doesn't ask for the mechanism, and that's going to go there to give us an OH. So we're almost there. So the intermediate we're going to have then is the hydroxynitrile. This is the nitrile. Right, let's just talk about the reagents and conditions for that first step. Right, it's not potassium cyanide, it's hydrogen cyanide. Or you can say potassium cyanide followed by HCl. You do need some acid in there to make that reaction occur. So you need to say HCN or KCN plus HCl. All right, so you're going to make this and the nitrile. Now, this is a hydrolysis reaction. And the conditions you need to turn a cyanide into a carboxylic acid is you heat with reflux with dilute hydrochloric acid, and that will hydrolyze the cyanide to the carboxylic acid. Include reagents and conditions. So we've done that heat reflux HCl. The type of reaction occurring, that's hydrolysis. Well, the type of reaction occurring here is nucleophilic addition. Right, the cyanide is the nucleophile, and it's addition because you break the carbon-oxygen double bond. You need a balanced equation for each reaction. So let's do the balanced equation. 7 marks, a lot of marks for this question. Right, so we're going to have cyanide. Sorry, we're going to have this plus HCN goes to CH3 CHOH CN. That's balanced, that equation. Don't need to do anything there. The hydrolysis one then is a bit more difficult. So we're going to have CH3 CHOH cyanide. We're going to react that with hydrochloric acid, HCl, or you can say H plus if you like. And what you're going to get is you're going to get the product. And we're going to get, also we're going to get the nitrogen ends up as ammonia there, NH3. Right, so you can see to balance that, we are going to have to put in, let's change that to H plus. Actually, the H plus doesn't need to go there because it's not a reactant, it's just a catalyst. So we just need H2O in there. And you can see we're going to have the hydrogens here. We've got 1 hydrogen there and 3 there, so that's 4 hydrogens. And we need 2 new oxygens there. So we're going to need 2 H2O to make that equation balance. That's the balance equation for that. Okay, so that is everything covered there. Right. And you can polymerize lactic acid to form polylactic acid as shown in the diagram. What kind of polymerization is occurring? Well, it is condensation, because what's happening, we've got one end, that's the carboxylic acid group. This is the OH group, and of course you've got kind of drawn the lactic acid round the corner there. Look, that's carbon atom number 1, number 2, number 3. And that is going to polymerize with the next one here. So they're going to go, the alcohol groups on the carboxylic acid groups are going to polymerize to form an ester linkage. So we're going to lose water there, lose that water molecule. So it's a condensation polymerization. Draw a circle around the repeat unit of the polymer. Okay, so right, I like to start at the new bond formed. So you can see that bond's going to break. So what I'm going to do is I'm going to draw that bit there. Right, now I need to go, this is the lactic acid. And I'm going to draw that there, because if we draw that, sorry, I draw my in slightly the wrong place, 1 minute. That's more than a repeating unit I've drawn there. I need to draw that there just to stop after the carbonyl. Okay, so, and then you can see that this oxygen here is the same as that one there, just repeats over and over again. So that's the repeat unit of the polymer. Right, this is quite a wordy question about identifying group carbonates. Okay, so a chemistry teacher found a bottle containing lumps of white solid. The original label was missing. Someone had written group 2 carbonate, the sort of thing that only happens in AQA exams. Okay, so they've got this group 2 carbonate and they don't know which one it is. Okay, now student 1 did one method to find out what the nature of the carbonate was. Obviously group 2, it could be calcium carbonate, it could be magnesium carbonate, it could be strontium carbonate. So they're doing experiments to find out which is the metal there. Okay, so student 1 knew the group 2 carbonate produces 1 mole of carbon dioxide. Okay, so I think he asks us later on in this question, but of course the reaction is going to be MCO3. And it's going to react with nitric acid, HNO3, and you're going to get MNO3 twice, because obviously the M is a 2+ ion, and you're going to get CO2 and H2O. And that's the important thing, is that 1 mole of the carbonate gives us 1 mole of carbon dioxide. So they're going to put in a known mass of carbonate in there. They're going to measure the volume of carbon dioxide produced. Then they're going to use, the number of moles is equal for a gas, 24 dm cubed is 1 mole. So it's going to do volume, number of moles is volume in dm cubed divided by 24. We're going to find out the moles of carbon dioxide. That will give us the moles of that. We also know the mass of that. If we know the mass of that and the moles of that, we can work out the MR of that. MR is equal to mass of the carbonate divided by the moles of the carbonate, which you find from the moles of CO2. Find out the MR. We know that the carbonate bit is going to weigh that weighs 60. So we subtract 60 from that, we're going to get the value, the atomic mass of M. We know the atomic mass of M. We can then work out the identity of M. That's what we're going to do. Okay, so let's just go through. That's what they're going to do. So you can read that question at your leisure. That's what they're going to do. Right, so mass of weighing. Right, so I've done this already, this bit. So the weighing bottle of the carbonate weighed that much when it was empty. So weighing by difference, it weighed that much. So what we're going to do, subtract one from the other. So that is the mass of the carbonate is 0.816 grams. The volume of the acid used, that should be in excess. Okay, so that doesn't really matter how much acid you use as long as it's in excess. And we make that volume of CO2. Okay, so question A, we've done that. Complete the mass of carbonate. Calculate the moles of carbon dioxide collected in the measuring cylinder. So, right, so we've got the volume of the CO2, 225 centimeters cubed, which is equal to 0.225 dm cubed. So the number of moles is equal to 1 mole occupies, so it's going to be 0.225. Sorry. So the moles of carbon dioxide is going to be 0.225 dm cubed divided by the volume of 1 mole, 24. That is equal to 9.375 times 10 to the minus 3 moles of CO2. That means that is the number of moles of carbonate we've got. Okay, what it says, calculate the molar mass of group 2 carbonate. So what we're going to do now is we're going to do, we said MR is equal to the moles, is equal to the mass divided by the moles, which is equal to 0.816 grams from there, divided by the moles of carbon dioxide is equal to the moles of the carbonate. So that is equal to 87.04. Okay, now MCO3, that bit weighs 60. So that means M weighs 87 minus 60, which is equal to 27. Okay, to two significant figures. And the closest one to that is not terribly accurate. The closest one, because that is obviously magnesium, has got an AR of 24.3. So we conclude from that experiment that the carbonate is probably magnesium. Calcium would be too high because calcium is 40.1 for calcium. So much closer to magnesium than it is to calcium. So there we have it there. Okay, so it's not that accurate, and there's some questions about accuracy. Okay, so student 2 carried out the same experiment using the same mass. He made no errors in the measurements or calculations, but obtained a value for the molar mass which was 10 grams per mole greater than the value obtained by student 1. Now, explain one procedural error. Okay, so what I thought, first of all, let's have a think about this. MR is equal to mass over moles. The value he gets for the MR is too big. So that means this moles, the mass is not going to be wrong really, but the moles of CO2, which is equal to the moles of carbonate, that is too small. So i.e., he hasn't collected all of the carbon dioxide that he should have collected. And the first thing that struck my mind was that maybe the acid wasn't in excess, okay, because it doesn't say he uses the same acid, right? But anyway, I looked in the mark scheme, and that's not really the answer they're looking for. That would, if you didn't have an excess acid, that would definitely cause that. You wouldn't release all the carbon dioxide, the number of moles would be too small. They're looking at something more simple than that. They just said, right, he didn't get the bung in the flask quick enough, and so a bit of the carbon dioxide escaped. A little bit of the carbon dioxide escaped. That means this number here is too small, which makes this number too big. Right, now the next bit here, which is kind of the sort of my original idea of what causing it is wrong, is it was discovered that student 2 had used 110 of dilute nitric acid instead of 100. Why would this not have affected student 2 results? So we obviously used an excess of acid, right? Because the amount of acid doesn't matter. You're adding excess of acid because, you know, you all we're worried about is that 1 mole of carbonate gives us 1 mole of carbon dioxide. And as long as you've got enough acid, and you obviously have got enough acid because he added even more than student 1 did, so that's not going to be causing a problem. Okay. The teacher noticed the group 2 student for group 2, he had it in powder rather than lumps. Would this affect the rate of reaction? Yes, of course it would. It would make it go much faster because you've got a bigger surface area. But would it affect the volume of gas produced? Not at all. You just produce the gas in a shorter time, but the actual volume, of course, would be the same. All that affects the volume of the gas is the mass of this magnesium carbonate. Right, now student 3 did it a different way. Right, what he did was he made the carbonate undergo thermal decomposition. So he started off with MCO3 solid. He heated it up, or she heated it up, and he got MO, the oxide, and carbon dioxide gas. So the mass is going to drop because you start off with the carbonate, and you're going to lose, all the mass you lose is due to the carbon dioxide, which has been liberated. So if you know the mass of carbon dioxide, that's the mass lost, you can work out the moles of carbon dioxide from that. If you know the moles of CO2, then you're going to know the moles of that. And then once again, we're going to do this. We're going to do Mr is equal to the mass divided to the Mr, the carbonate is the mass of the carbonate, divided by the moles of the carbonate, which is equal to the moles of the carbon dioxide from there. So it's pretty similar from there on. Okay, so what he did was, right, so again, I've done this bit. Empty test tube weighed that much. Before the experiment, when it was a carbonate, it weighed that much. Afterwards, it weighed 20 point. Okay, so we can work out the masses of those carbonate and the oxide by subtracting the mass of the test tube. So that means the mass of the carbonate was 0.451, and this one was 0.209. Write an equation including state symbols for the thermal decomposition of group 2. Well, I've done that there. Okay. That's quite important because it gives us that 1 mole of carbonate gives 1 mole of carbon dioxide, and use the result to calculate the molar mass of the group 2 carbonate. Okay, so what we're going to do there, from these two, we can see that the difference in mass here is equal to the mass of carbon dioxide produced. So that's going to be equal to subtract 209 from 451, you get 0.242 grams of carbon dioxide. So we can say, therefore, moles of carbon dioxide, 0.242 over the MR, which is, of course, 44 for carbon dioxide. So the moles of carbon dioxide we've got is exactly 5.50 times 10 to the minus 3. Okay, so that means the moles of MCO3, now this is where you can do it in two different ways actually. The moles of MCO3 is equal to that. And also the moles of the magnesium oxide is also equal to that. Right, let us work with the carbonate, okay? To find out, we're going to find out the MR of the carbonate. So MR of the carbonate is equal to mass divided by the number of moles. What was the mass of the carbonate we had? It was 0.451. And divide by 5.5 times 10 to the minus 3. And that gives us an answer of 82. Now, I say we've chosen we've chosen the carbonate there. We could equally well do it with the oxide and find the MR of the oxide, which should give us exactly the same number. I'll just do that one as well. So the MR of the oxide is equal to the mass, which is the oxide is 0.209. The moles of the oxide are the same, and that is also equal to 82. Right, so now we need to say what is the nature of the carbonate. So we've got MCO3, the MR is 82. The carbonate bit weighs 60. So that means that the take away 60 from 82, the AR of the metal is 22. Okay, and again, the closest one you can get to that is magnesium. The AR of magnesium is 24.3. So, and calcium is 40. So we conclude that that is almost certainly it's going to be magnesium and not calcium. Okay, so let's have a look here now. It says, right, student 3 used the same balance as student 1. Give a reason why the mass of the carbonate measured by student 3 has a greater percentage of uncertainty known than student 1. So student 1's the one who did it with the gas volume, okay? He weighed out that much, he weighed more. Well, let's say that the accuracy of the balance was, plus or minus 0.001 gram. Well, 0.00, so the percentage error for this one is going to be smaller. The percentage error for student 1 is going to be 0.001 over 0.861 times 100. And you can see that is going to be a smaller number than if you're dividing it by the other student. He only weighed half the amount. So he's weighing half the amount, more or less. So his error is going to be, the percentage error is going to be twice as big there. And really, the percentage error for each of the students is going to be very, very small. It's not really an issue, okay? But of course, it would be an issue if you were measuring out masses like 0.005, then and the balance is only accurate to that much, then you are going to be out by times 100. That's equal to a 20% error, which is huge. So you shouldn't use a balance of that accuracy to measure out such small quantities of that. Anyway, this student, lower error because he's weighing out a larger mass of the carbonate. Okay, now student 3 noticed that on heating the test tube, some solid was lost. Explain how this would affect the calculated value for the molar mass of the group 2 carbonate. Okay, so what we're going to say is we said there that moles, MR, is equal to mass over the moles of the carbonate. The moles of the carbonate we're going to use there is equal to the moles of CO2. And 1 mole of carbonate gives 1 mole of CO2. Right, here we're going to overestimate the moles of CO2 because a lot of the mass we've lost is not due to CO2 really, it's due to bits of solid. So we're going to overestimate the moles of CO2. That means we're going to overestimate that. It's going to be too big. That is going to have the effect of making our calculated value of MR too small. So it'll be a bit smaller than it really is, the molar mass of the carbonate. Okay, I think that is the end of that question. Yeah, this is a bit more interesting about NMR. Okay, we're going to use NMR to distinguish between isomers of C6H12O2. Okay, so first of all, a few normal background questions on NMR. Tetramethylsilane is the standard when with 1H and 13C spectra. What's the formula of tetramethylsilane when you have a silicon there, and you have CH3. Be careful that you have 4 methyl groups around it. Doesn't ask for displayed formula, so you don't need to show every bond. That is the structural formula of it. TMS is inert and non-toxic. State 2 other reasons why TMS is suitable for a standard when recording NMR spectra. Right, the best reason to say is that you're going to say that the nuclei, whether it's 1H or 13C, are more shielded than almost any other than the nuclei in almost any other compound. So that means the peak for the standard when you get your spectra, okay, this is ppm here. When you're going that way, these are de-shielded nuclei, and the highly shielded ones you find down here. So that means your TMS peak is going to be at the right, away from all the peaks in your sample. So you're not going to get mixed up. You know, it's not going to be in the middle there like it was that red one, which would be mixed up. It might overlap with one of your real peaks. So it's going to be, because it's more shielded, it'll be to the right. That's the most important reason, I think. Or the second most important reason is that this will only give one signal. We're going to give one peak, whether you're using it for the hydrogens, because all those hydrogens are all equivalent, and they won't split either. One peak in 8 and no splitting. And the same in 13C. All those carbons are all equivalent, so you only get one peak in 13C. And of course, you don't get splitting in 13C anyway, so that's not an issue. So they're the 2 reasons I would give. There are other reasons, things like, well, they've given 2 that it's inert, so it's not going to react with the thing. There are other reasons, but they're the 2 most important reasons why that's used. Okay, so draw the structural formula of 2 esters with the formula C6H12O2 that only have 2 singlet peaks in the 1H, okay? Now that is an awful lot of protons, 12, to give only 2 peaks. So that means you're going to have a lot of protons which are equivalent. Now, that always makes me think, right, if you have methyl groups, right, attached, those 6 protons are all going to be the same. Well, let's make that 9 protons. We can have that, can't we? Okay. And also, this is particularly good because those protons is going to give you an integrated value of 9. And it will be a singlet because the carbon next door, this one, hasn't got any hydrogens attached to it. So that also, you can have that. And it doesn't matter what you stick it to. That's always going to give you integrated 9. And it's going to be a singlet peak. So that's 9 of our 12 protons accounted for. Okay, so, well, the other 3, that's obviously going to be a CH3, isn't it? It's got to be an ester, so we've got to have an ester linkage in. So all we've got to do is put all that together. That would give us 2 singlet peaks, this CH3 there, and then those 9 on the right. It says 2 esters. Well, that's pretty easy because all we've got to do is flip the ester around. So instead of having it that way around, we can have it that way around. That's our 2 esters. And it also gives us the peak areas are 3 to 1. Okay, so that's the integrated 9 to the peak area, and this is going to be integrated value of 3, 3. So that's all good. Right, the high resolution proton NMR spectra for another compound of another isomer of C6H12O2 is shown. Right, now show these data are consistent with the displayed formula. Okay. And that's the displayed formula there. So I'm just going to, so you can see, I'm going to just cut that out and put it to the side. Okay. So that is going to go, I'll put it there. Right, we've got to show this is consistent with that. Okay. So the ratio of the number of protons here of the peaks, so it's referring reading left to right, is 2, 2, 2, 3, 3. So I've written them above the peaks there. The CH2, that'll be 2 protons, 2 protons. This is a CH3 and this is a CH3. Okay, let's have a look at this one first here. So we've got to refer to the 5 all the chemical shifts for everything, okay? and 2 of the splitting patterns. Well, I'm going to do all the splitting patterns and all the chemical shifts because it's then you can take your pick which ones you want. Right, this singlet here, okay, that is going to be that methyl group because the carbon there is right, you've got three hydrogens and it's not next door. The carbon which it's attached to hasn't got any hydrogen, so that's going to give us, you know, the n+1 rule. We're going to get a singlet. The ppm of that is going to be about 2 because whenever you have hydrogens like these which are attached to a carbon that's next door to a carbonyl, if you look at your data sheet, that's always ppm 2. Right, which brings us to this one here. So that's going to have a ppm of about 2 as well. You can see, and this is what's always a bit higher. The ppm is a bit higher for a CH2 than it is for the equivalent CH3. And what's going to be the splitting of that? Well, look at the carbon next door, which is that one. It's 2, so that's going to be a triplet, n+1 rule. Right, let's have a look at that one. Right, so this one here, right, that's also going to be a triplet because the green ones are splitting it into a triplet, 2 carbons on the hydrogen there. And being next to that oxygen is going to give it a ppm of about 4, and it has got one of about 4, just below 4 there. There we go. Right, this one here is also going. This is another CH2, integrated value 2. That is going to be a quartet because the one next door has got 3 carbons next to it, so that's a quartet, and the ppm is next to the oxygen there, so it should be about 4, and it is about 4. Finally, we have got, running out of colors now, another left of black this time. Okay, that is going to be an integrated value of 3. It's not really near any electronegative group, so the ppm will be about 1, which it is. And you can see that it is split into a triplet because the carbon next door, the purple one, has got 2 hydrogens. Okay, again, you don't have to mention every splitting, but you do have to mention all 5 chemical shifts. Okay, there are 3 other isomers of C6H12, which are carboxylic acids with 5 peaks in their carbon-13 spectra. Okay, we've got to try and work out what they are. Okay, right. Right, so if we have, let's just think here, we've got 6, if we put 6 in a row, so it's hexanoic acid, 1, 2, 3, 4, 5, 6, right, that would give us 6 peaks. 1, 2, 3, 4, sorry, 1, beg your pardon, 1, 2, 3, 4, 5, 6 peaks. So that's obviously not one of them. So we're going to have to put branches into it to make it so that we've got just 5 peaks. So we're going to have to make 2 of those carbons the same. Now, to me, the most obvious way of doing that would be to, let's make it 5 long. And let's put another methyl group there. Okay, so that means that these 2 carbons are going to be the same of each other. So that's 1, and then that'd be 2, 3, 4, 5 peaks. Obviously, you've got to put all the hydrogens in there. That's one of them. What else could we do? Right, I think you could also let's see what happens if we put in a methyl there and a methyl there. So we've got 6, that's the carboxylic acid. How many peaks would that give us? Well, it would give us 1, 2, 3, 4, and then these 2 are going to be the same. That would also give us 5. And then you can probably see the third one. They don't have to give the third one, but all we've got to do is move these 2 green methyls along one. So we do that. See what I mean? We could have, so we've got butanoic acid with methyl groups there and there. That's going to give us 1, 2, 3, 4, and these two are the same, 5 peaks. So obviously you're going to put the hydrogens on those. You can't just leave it with carbons, but that's, you get the idea. Okay, draw the skeletal formula of a cyclic diol of C6H12 that's only got 2 peaks in its carbon-13 spectrum. Right, so to have so few peaks, we're probably going to have quite a bit of symmetry there. So let's put, oh, by the way, if you have it cyclic, that would mean, that would account for this carbon to hydrogen ratio there, which is CnH2n, not +2. Okay, that means you lose 2 carbons when it's a cyclic. Right, so let's put an OH there. Let's make it symmetrical to start off with, and an OH there. Now, we can see that these 2 carbons are going to be the same as each other, and you can probably see that all the other 4 carbons are all the same. There's no difference between them, they're all the same. So that would, those carbons there, the green ones, they're all the same as each other. They're all next door but one to the next door to the OH carbon. So that would just give you 2 peaks. So that's the answer there. Right. Let's just see if you didn't do that first of all, which would be the logic. You know, you've got to think in terms of being symmetrical. Let's see if you put an OH there and an OH there. Well, yeah, that would give you, those 2 would be the same. Then these 2 would be the same, and those 2, that would give you 3 peaks. It's not going to work. Okay, I think if you did it with the other thing is you could have them one there and one there. That would give you more peaks. So you'd have those 2 be the same. That yellow one, that would be different. That'd be unique. And then you'd have those blue ones would be the same. And finally, that green one would be unique. So that would give you 1, 2, 3, 4 peaks. So this is our answer, 2 peaks. That's a fairly standard question, really. Okay, so transition elements, they're ions and they're complexes. The oxidation state of vanadium in the compound NH4VO3. Well, we know that the ammonium ion is always NH4+. So let's do that. So that means this VO3 ion must have a charge of -1. Then we're going to use sum of the oxidation numbers is equal to the charge on the species. So the charge is equal to -1. Let's say the oxidation number of vanadium is V. Oxygen has always got an oxidation number of -2, so that's going to be 3 times -2, -6. And then to add 6 to both sides of the equation, you get V is equal to +5. Oxidation state of vanadium is +5. Okay. Now, zinc powder is added to acidified ammonium vanadate, that's called. So it's only the VO3+ ions we need to worry about. Okay. Now, use the data in the table, explain the sequence of reactions that take place. Now, you've really got to know here that, okay, all right, they've written it down. It's VO3. All right. So what I'm going to write down is the oxidation states of the vanadium species there. Okay. Right, this one is well, the VO, that's +5. What's it here? It's +5, and that's colorless or pale yellow. Now, this one, VO2+, that is actually, work out the oxidation number there, it's +4. You've got to know these really. So, and that, you need to know the color of that. That's kind of sky blue, or just blue. Then V3+, the oxidation number there is +3. That's green. And finally, the V2+ ion, +2 oxidation state, and that's violet. Okay, so we're going to see what happens when we add zinc powder to the VO3+ ion. in your answer, you've got to include, say what you'd see and the relevant ionic equations with their calculated E cell values. Okay, right. So let's just do E cell is equal to E right, which is the most positive, minus E left, which is obviously the most negative. Right, so let's see what we can predict what would happen. Right, so we need to look at, right, first of all, the VO3 plus equation, which you've got there. And we're comparing that to the zinc equation. Now let's see which is the most negative. Clearly the zinc is way more negative. So then the zinc is going to be best at giving out electrons, pushing away electrons. So that's going to go backwards, giving out those electrons. And this one is going to go, is most positive. So that's going to take in the electrons, the electron from the zinc, and go forwards. Okay, that's what's going to happen there. What would E cell for that reaction would be? Well, the right hand side electrode is the more negative, which is the zinc. Sorry, the right hand side is more positive, which is the vanadium. So we're going to have 1 minus 0.76. So that's plus 1.76 volts is the voltage for E cell for that equation. Balance the equation for that. Well, we're going to have to multiply this one by 2 because that's only one electron process. So we're going to have 2 VO3 minus plus 8H plus zinc this time goes to 2 VO2 plus and 4 H2O, and we're going to get Zn2 plus ions. That's our equation there. Okay, that's our ionic equation for that one. Right. Now, in doing so, we have formed this species VO2 plus, and look, we've got a half equation here. And so let's see what would happen there. Can the zinc then react with that? And we can see that the zinc would react with that because once again, look at these two. We've got the zinc and the zinc, sorry, and the vanadium, the VO2 plus one there. Zinc is way more negative, so that's going to go backwards. That's going to give out the electrons. This is more positive. That's going to go forwards. It's going to take in the electrons. Let's do E cell for that one. I'm going to make space here. Okay, let's get rid of all this. I'll leave the E cell bit. Sorry. I'm doing here. Sorry about this. Right, okay. So let's get rid of this. And that. Right. So we write E cell for that. We're going to get E right is this one, plus 0.34 minus 0.76 for the zinc. And that is going to give us 1.0 volts exactly. Now let's write the half equation for that. Once again, we're going to have to multiply this one by 2 because this is only a 1 electron process. So we're going to get 2 VO2 plus, oh, we need to take the colors here as well. Okay, so in the first equation, we would see, well, let's just write this equation and go back and do that. We're going to get 4H plus zinc. It's going to go to 2V3 plus 6H2O plus zinc 2 plus. Right, well, in this equation, we're going to see this will be a blue solution, and what happens, it will turn into a green solution as the zinc reacts with it. Okay, so the blue will gradually go to green. In the previous equation, this one was yellow, and it gradually turned into a sky blue solution. That's what happened there. So so far we've seen our solution go from yellow to blue and now to green. Okay, and there's still more things that happen. We'll see now. So just clear some space. Right, so we've now got this VO2 plus, V3 plus formed. We've now got the V3 plus, but let's have a look at the half equations. You can see again, we've got V3 plus up here, yeah? And it's going to, can that react with zinc? Well, it's negative, but it's still much more positive than the zinc. So the zinc's most negative, minus 0.76. So that's going to go backwards, giving out the electrons. This one is more positive, so it's going to take in the electron, going forwards to form V2 plus, which is the violet one. So we're going to see this go from green to violet in this step, and we'll see it will be the last step as well. All right, let's do E cell for that. Well, we've got the most positive, which is minus 0.26 minus 0.76 for the zinc, so that gives us plus 0.5 volts for that one. That's E cell. Right, the equation. Right, once again, we're going to have to multiply this one by 2 because that is 2 electron process. The zinc is only 1. So we're going to have Zn, this one going forward, Zn plus 2V2, 3 plus, sorry, goes to 2V2 plus and Zn 2 plus. So we're going to see the green solution go violet here. Now let's see if anything else will happen. So let's clear this. We've got our violet solution. Is that going to react? Let's have a look. So we have got the half equations we're interested in here are the zinc one again, and this one V2 plus going to V. Now, which is the most negative here? Well, in this time it's not the zinc one, it's this one here. So that one would go backwards and that would push the zinc to go forwards. So that means that zinc metal would not react with V2 plus. No reaction there. So you would not see the violet color disappear and vanadium metal be deposited on the surface of the zinc. That doesn't happen. The solution just stays violet, and that's the end of the reactions. Okay. This is a straightforward recall question now. It just says, explain how the vanadium 5 oxide can act as a catalyst in this one step of the contact process. Okay, so you need to know the formula of vanadium 5 oxide, which is V2O5, and you've got to know that really. V2O5. Now what happens is V2O5 oxidizes SO2 to SO3, and it becomes reduced itself to the vanadium 4 oxide. And then in the next step of the reaction, the vanadium 4 oxide reacts with oxygen, and that oxidizes it back up to vanadium 5. Okay, so again, those two, so and you can see that the vanadium 5 doesn't actually get used up in this because it gets regenerated, so it's acting as a catalyst. The overall reaction is just that there. Okay, describe the reactions of separate portions of aqueous copper 2 ions with aqueous sodium hydroxide with excess. So we want copper 2 ions, and of course in solution they are going to be hex aqua, H2O6 2 plus. We want the reactions with aqueous sodium hydroxide, which is OH minus, or with NH3, or with hydrochloric acid, and what's going to react with there is this chloride ligand. Okay, and your answer should link observations with equations and include the formula of any copper complex ions, including state symbols. Okay, let's do the sodium hydroxide first. Okay, so what happens is copper, it doesn't ask us to explain, but of course this is a Bronsted-Lowry acid, this complex, because it tends to donate protons, because the copper draws in, the copper 2 plus draws in charge from the water molecules, makes it easier to release H plus. So what happens is if you add OH minus to that, it will release 2 protons, and you'll get, so 2 of the waters will turn into OH minus because they've lost an H plus. It's an acid-base reaction, and this is a pale blue precipitate. That's what happens there. Now, if you add excess aqueous ammonia, and we should do this in one step, I think, it's With excess aqueous ammonia, what will happen is the ammonia ligands will push out some of the water ligands, 4 of them in fact. So you're going to get H2O, that should be a 6 there, sorry, not 2, 6, 2 plus. We're going to have, so it's a ligand exchange reaction. We've got 4 ammonia, which can act as a ligand, of course, because the ammonia's got a lone pair on the nitrogen. And we're going to push out 4 of those waters. So we've only got 2 left. And we've now got 4 ammonia ligands, and that is soluble, and it's a very dark blue solution. That's what happens there. Okay. Both of these have got coordination number of 6. So they're going to be octahedral, these complexes are all octahedral there. Now let's see what happens with the hydrochloric acid. The conc hydrochloric acid, well, you've got a very high concentration of chloride ligands. So what happens is you push out the water ligands and you replace them with chloride ligands. But because the chloride ligands are bigger, you can't fit 6 of them round, you can only fit 4 round. So you're going to get CuCl4, 4 ligands. Now the oxidation state of the copper hasn't changed, it's still +2. Each of those chlorides is -1, 4 times -1. So the charge on the species is 2-. And the shape of this is actually tetrahedral, it doesn't ask you for the shape, but it is. And you're going to get 6 water molecules being released there. And this is, I should say what color, this is blue solution, copper. These are all blue, aren't they? Sort of turquoise blue. When you add this complex is green stroke yellow. So it will turn a sort of emerald green color there. So that is all you need to write for that there. It's a fairly recall sort of question. Okay, I'm going to leave that there and continue with that paper in the next video.